Let's do a Biot-Savart law example. We have a straight wire with a half circle in it of radius r, with current I flowing in the direction indicated, from bottom to top. We'll find the magnetic field at the center of the half circle. Dealing with the Biot-Savart law is much like dealing with Coulomb's law, in that most of the work is associated with figuring out the dl and the r vector. This particular wire has three distinct regions: the straight part above, the straight part below, and the semicircle. Let's mark out an arbitrary dl on the straight part above and the corresponding r vector. Something very nice happens here. See how the r vector and dl are parallel? That means dl cross r will be 0. And that means that no part of the straight wire will contribute any magnetic field to the total, and we can ignore all of it. Instead, let's focus on that half circle and mark out an arbitrary dl there. I've indexed that dl with the coordinate theta as shown. There's nothing saying you have to use this definition of theta, but whatever you do, make sure that the trig in the steps that follows is consistent with your definition. For example, let's figure out the r vector. When I'm building up a vector from scratch, what I like to do is put down a little template. Our r vector has components that point in the I hat and j hat directions, and it looks like it's going to be pointing down and to the left, so the I and j terms will both be negative. Those components are parts of a vector of magnitude capital R. And one will go like cos theta, while the other goes like sine theta. Now, just to make things as explicit as possible, I'll invoke a little bit of geometry to note that this angle over here is also theta, and work my trig factors from there. If you want to double check your work, imagine what happens when theta is 0. In that situation, the r vector should point straight down, and the horizontal component should shrink to 0. Cos 0 is 1, and sine 0 is 0, so it all checks out. Now, a couple of you might be complaining that one of my steps appears to only work for certain angles. If my dl were down here, so that my theta was greater than 90 degrees, wouldn't the r vector have a positive j hat component? Well, that's certainly true, but fortunately the trig factors take care of that for us. Cosine of an angle between 90 and 270 is negative, and that fixes things for us. In fact, as long as you do the geometry for problems like this with a theta that's in the first quadrant, between 0 and 90, it all kind of works itself out in the other quadrants. Okay, next up we need a dl. I'll set up a template again. My dl has I hat and j hat components, and for the dl indicated, it points up and to the left. So I throw in some sines. Now I want to write everything in terms of thetas and d thetas, so I'll take advantage of the fact that my dl is a little chunk of a circle, which is to say it's a little chunk of arc length. And arc length is radius times angle. So a differential arc length, the length spanned by a differential angle, is radius times d theta. Thus I put in the magnitude of dl in each term, and all that remains is to figure out which one goes like sine and which one like cosine. I suggest making a bigger picture so that we can do some careful geometry and find out how theta is arranged with respect to dl. Note that dl is tangent to that circle, and so it makes a right angle with that r vector. Now we can mark out the components of dl and walk theta over. So that's the angle associated with dl that's actually equal to theta, meaning the I hat component of dl goes like cos theta, and the j hat component goes like sine theta. Okay, so now we get to take the cross product of dl and r. You can do cross products with determinants, and do feel free if that's what you prefer. But if you're using ijk vector notation, there's an approach that's often quite a bit simpler once you get used to it. We're taking the following cross product. And a cross product is just like any other product in that it distributes. So we can FOIL this out. The I hat term crossed with the I hat term gives 0, and so does the j hat cross j hat term. That leaves two non-zero terms. To use this cross product approach, you need to be able to keep track of which unit vectors cross to form which unit vectors. There's a little mnemonic I like to use. If you look at I, j, and k in alphabetical order, and allow yourself to go around the corner, you can read cross products right off. I cross j is k, j cross k is I, and k cross I is j. If you go backwards, you pick up a minus sign. J cross I is minus k, and so on. With that in mind, we put it all together. And there's our favorite trig identity. Cos squared plus sine squared is 1. Now the magnitude of the R vector is not too hard if you just refer to the picture. It's just the radius of the semicircle, big R. Time to stack up everything. With theta defined the way we have it, the bounds for a semicircle should be 0 and pi. And there it is. So to recap, using the Biot-Savart law involves lots of vectors, lots of geometry, and a cross product. But if you take your time and lean heavily on diagrams, it can be done.